Good afternoon, everybody, and thank you for this invitation to come and talk to Upholland U3A. So yes, this is the weird world of the very, very small. And my research in past years has involved looking at things on the scale of nanometers, or basically molecules and atoms. And that's what I'm talking about this afternoon. So I'll try and start with just very briefly giving a sense of scale down to the world of nanometers, billionths of a meter. And I'll say something about how we try and figure out what the world is made of. In other words, we use the symmetry of what we see in the ordinary world, in the macroscopic world, to tell us something about what the world is made of, i.e. the fact that atoms exist. And then I'll finish by talking about the quantum world and how we can actually see, or how we can build microscopes to image individual atoms. So we're used to the idea on a macroscopic scale, on a world of meters or possibly kilometers, and the smallest thing we can see with our eyes is perhaps a fraction of a millimeter or so in size. So we're used to the idea of being able to see something as small as an insect. Anybody recognize what this is? If we go down a little bit smaller than a millimeter, this is a pollen grain, okay? And this is about a 20th of a millimeter in size. And that is pretty much too small to see. Most people, unless they've got really good eyesight, would fail to recognize a pollen grain, certainly not in the sort of detail you can see in this microscope image. So 1/20th of a millimeter, that corresponds to about 50 microns, a micron being 1,000th of a millimeter. But we're going to go down even smaller than a micron. We're going to go down to units that are 1,000 times smaller than a micron. Just shortly, we'll get down to the scale of nanometers. So it is possible for mankind to build mechanical objects on a scale of micrometers or microns. We don't often do that because you're used to the idea of building small things, but not mechanically small things. We all are aware of the fact that if we move over to electronics, then of course we can pack an enormous number of objects down to a very small size. You know that from the amount of computing power that you may or may not be carrying in your mobile phone around with you. So it is quite probable that a little bit of silicon inside your phone, inside your tablet, inside your laptop, whatever, a few square millimeters might have many, many millions of transistors on board. These days, it is not unusual to have a chip on board your mobile phone that might have 1 billion individual components occupying an area of only a few square millimeters. That means the individual components, in this case transistors on the electronic chip, might only be 10 to 100 nanometers in size. And these days it's closer to 10 than it is to 100 nanometers. So even with everyday technology, we're already getting down to the point where we're talking about objects that are only tens of nanometers in size. But we can ask the question, okay, we sort of understand the world around us. We know, in a sense, what things are made of, but how can we tell what that is made of? We might look at things like wood or brick or metal or plastic, and we can ask the question, well, what is that actually made of? How much can we go down that limit of, if we take this object and cut it in half and cut it in half again and cut it in half again, how far can we go before it's no longer the object we started with? How can we tell what the world is made of? What clues do we have when we look around us? Well, this is a question that's been thought about for millennia, of course. Aristotle started saying, well, everything is made of earth, air, fire, and water. A very nice, simple system, and there are arguments as to how if you take fire, air, earth, and water in the right proportion, then you can get everything that we see around us. But it turns out that that is too simplistic. The world is a little more complicated than that. And it wasn't really until Galileo came along that we started to address it scientifically. In other words, Galileo was the first person really to say we should determine what the world is made of, or we should answer any question by doing experiments, quantitative experiments, measuring something rather than qualitative intellectual arguments. In other words, we should ask what happens if, rather than what should happen. So the earlier Greeks might say, well, if you let go of this object, it should rise if it's light and it should fall if it's heavy. But Galileo said, well, let's actually measure things and see what the answer is, not what you might expect the answer to be. So that was, if you like, the start of scientific reasoning. And of course, if we move forward, then we get Newton, who basically established this is the way the world seems to work. The laws of motion, the law of gravity, experiments on the nature of light when he went back to Woolsthorpe Manor during the plague of the 1660s, and he was in lockdown. Sound familiar? Yep, okay. So this is Newtonian mechanics, classical mechanics. The mechanics of 300 or so years ago is where we were at and where we have been for quite a while until the turn of the last century or so. So we thought we understood how the world worked, and we thought we understood, for instance, how the solar system works. Everything appears to be clockwork. As far as Newton is concerned, everything is clockwork. For instance, if we look at the planet Jupiter and say, well, the Jupiter is there now and it seems to be moving like this, then using our understanding of, for instance, the law of gravity, then we know where Jupiter is going to be a day later, where Jupiter is going to be a year later, or 100 years later, or 1,000 years later. Everything works by clockwork. And that's where we thought we understood how the universe worked as of a few hundred years ago. But when it comes to actually trying to understand what things are made of, if we look, for instance, at snowflakes, we see they're all different, but they all have this six-fold symmetry. So surely that must be telling us something about what a snowflake is made of. We don't have to be able to cut it apart necessarily to be able to say whatever the building blocks of a snowflake are, surely they must have some six-fold symmetry. How else can you explain the fact that every snowflake comes out with 6 arms or six-fold symmetry? So we can use clues from the macroscopic world to start asking the question, yeah, okay, maybe the universe is clockwork, but can we actually start going inwards rather than think about how the planets go around the sun and what sort of galaxy we exist in? Can we ask the question of what is stuff made of here on Earth? So we look at snowflakes and we get the hint that something inside a snowflake must have six-fold symmetry. And we look at other crystals. Doesn't really matter which one this is, but we look at this particular metal and we see lots of straight edges, implying that whatever the building blocks are for this, whatever the Lego bricks that make up this metal, they presumably are arranged in some fashion that explain why we get these strange L-shaped or square-shaped objects within this particular crystal. And here again, another crystal which appears to be occurring naturally in blocks of something that looks like cubes or cuboids. So presumably, whatever the Lego bricks that make up this material, they must have a similar shape to explain why they lock together and form these particular crystals. Yet along comes a different crystal. That's a dodecagonal crystal. It's a crystal with 5 sides on each face, so we've got lots of pentagons. What must the building blocks of that be in order to explain how we get pentagons? Getting squares and hexagons, well, you can just about understand squares and hexagons, because if you look at most bathroom tiles on the floor, they're made of squares or they're made of hexagons, and we can see how they all fit together to make a larger structure. But how can you put pentagons together to make a pentagonal crystal like that? So that was somewhat confusing. But the bottom line is always these structures are giving us clues as to what the world must be made of. They must be telling us something about the underlying structure. So how did that process work? I'm not going to go through all of the steps. Here I've got a timeline of 300 years from 1600 to 1900, giving photographs of a few of the key players who helped us understand what must the building blocks of matter be in order to explain the world around us. Most of the clues came from either looking at crystals and judging what the building blocks must be, or came from chemistry. If you react this material with that material, you get this much of this material, and you can start to piece together what must the building blocks be in order to explain chemistry, or originally alchemy. So on the very left there we've got Democritus, who was the first to think, well, maybe you can't keep cutting an object in half again, in half again. Ultimately there will be some smallest building block called atoms, indivisible. So he doesn't belong in 1500. He's way off the left-hand side of this particular diagram. But maybe, perhaps, you might recognize some of these faces. So I'm not going to talk about their contributions, but let's just go through who these people are. Boyle, we've already met Newton. At the bottom there we have Lavoisier. Here we have Dalton. Here we have Avogadro. Here we have Maxwell. And here we have Boltzmann. So all of these people made a contribution to try to understand what are the building blocks, what are these atoms that the Greeks referred to, and what must they be in order to explain how matter is put together. Two important results that came out of the 1800s, I'm picking out two as being rather fundamental. One was the work of Young, who showed that by shining light through slits, it has interference properties, just like water waves on the surface of the sea. So he determined that light basically has a wave-like property. Light is made of waves. This is an important observation. Later in the century, along came J.J. Thomson, who basically said, right, matter is partly made of these particles, which we're going to call electrons. So the building blocks of matter, whatever they are, must comprise electrons plus something else. Electrons are negatively charged, whereas ordinary matter is neutral. So there must be equal amounts of negative and positive charge. So although as of the 1870s, electrons had been discovered, it was assumed that there must be other particles out there. There must be other particles inside atoms, because otherwise all the electrons would repel each other, because it was known that that equal charges, the same charges repel each other, different charges will attract each other. So the world can't be just made up of electrons, there must be something else out there. But as of about 1900, it was established that stuff, matter, is made of atoms which must comprise electrons and something else, and light is made of waves. That took a little while to sort out, but after 1900 there was absolute chaos, because for the next 10 years or so, I haven't covered the entire century, you notice, this is only 30 years from 1900 to 1930, suddenly a lot of people were making a lot of discoveries about the nature of matter, which threw up into the air a lot of what we thought we understood. And certainly a lot of what we thought we understood from Newton had to be thrown out, and we had to start again. So again, this is some of the key players placed roughly on a timeline of when they made major contributions. And again, you might recognize some of these. Let's play the same game again. Who have we got here? Becquerel, and then we have Planck, and we have Rutherford, and then we have, I'm sure you recognize Einstein, then we have Niels Bohr, then we have de Broglie, and then we have the architects of quantum mechanics, Heisenberg and Schrödinger. So quantum mechanics is what we ended up with after 30 years, which is basically a description of pretty close to everything. In other words, what all matter is made of. And the important discoveries that occurred during those 30 years, I'm not going to assign a discovery to each individual. I'm just going to indicate the discovery on a timeline. Radioactivity was discovered. Then it was realized that light is actually particles. The existence of atoms were confirmed, as was a positively charged nucleus. Then it was realized that probability plays a key role when looking at atoms. Electrons were determined to be waves, and that resulted in the construction of what we now call quantum mechanics, a theory which says this is the way the world is. Notice that in the previous century it was determined that light was a wave, but now it's been established that light is a particle. And previous century it was determined that electrons are particles. Now it's determined that electrons are waves. Huge amounts of confusion. Are they particles or are they waves? The answer is yes. In the sense of on Tuesdays and Thursdays they're particles, but on Mondays, Wednesdays and Fridays they're waves. In other words, you cannot pin these things down. So it's no surprise that this was a very confusing time. And it wasn't until Heisenberg and Schrödinger pulled all of this together and said, look, we now have a coherent way of describing what atoms are, how they're put together, and how these atoms build up all of matter. But whenever you try and teach the birth of quantum mechanics, it was a very confusing time, because year after year after year, new discoveries were being made about the nature of what an atom is. So we now think one way of visualizing an atom is to say, right, the fundamental building blocks of all matter is an atom which is made up of a positively charged nucleus and lots of negatively charged particles called electrons zooming around them like bees in a beehive. So that's the sort of classic, if you like, iconic way of thinking about an atom, a little nucleus and a buzz of electrons around them. And that worked for a little while in the sense that in the early parts of the 1900s, that was the sort of picture that people had in their heads. But the main problem with that particular picture is it doesn't tell us that all the electrons have different energies. This is crucial in the sense that if you look at that picture, you see, okay, there appear to be, how many are there? Five electrons buzzing around there, and they seem to be all the same. You would expect all of those 5 electrons to be moving with the same speed and have the same energy. But in order to explain the elements in the periodic table, hydrogen and helium and boron and lithium and all the way up to uranium, we need a model that goes beyond this picture. We need something in which all the electrons have different energies, and then we can start to explain why all the elements are different. So we need a slightly modified version of that same picture, and one way of modifying it is to say, well, it's not quite a solar system, but we can think of the electrons as orbiting around a central nucleus, and rather than buzzing all over the place and all being at the same distance from the nucleus, let's think of some electrons being close to the nucleus and some electrons being further out, in much the same way Mercury orbits close to the Sun and Pluto orbits a long way from the Sun. Now that's a two-dimensional picture, a sort of flat pancake, and we know that atoms are effectively three-dimensional objects. So although that picture held for a while, that's simply a two-dimensional representation of how electrons exist in an atom. We should remember that in fact they're in shells, so that picture is good in the sense of the shells, but the shells are three-dimensional, and here the shells have been cut through like a Russian doll to show that there are shells inside shells inside shells. So at least this gives us now a clue that different electrons are different distances from the nucleus, and they have different energies, and so different elements, hydrogen, helium, lithium, boron, etc., correspond to different numbers of electrons with different amounts of energy, and then we can start to explain why we have a periodic table of elements. So I'm not going to go through all the details, but the periodic table of elements is periodic because when we look at the number of electrons that can be in a given shell, there are a very specific set of rules that say you can't have any number you like of electrons, let's say, in the green shell or the blue shell or the yellow shell. You can't just stuff as many in as you like with a shoehorn. There are particular rules that say this shell can only have 6 electrons, or this shell can only have 8 electrons, or 10 electrons, or 14 electrons. And that is why we get the periodic table of the elements, where the characteristics of particular elements, like for instance copper and silver and gold, have a similar set of characteristics, a similar set of properties, properties being density and magnetic properties and chemical properties, and these repeat every certain number of elements because of the number of electrons that are in these shells. So as soon as we have a model in which we have a central nucleus and shells of electrons in which we have a particular number in each of those shells, then we can explain the periodic table. It didn't quite happen in that order because people started putting the periodic table together and then realized there were particular elements we didn't know about that could be predicted based on their position in the periodic table, and that helped to actually generate the concept of what we now call the Bohr atom, with a nucleus surrounded by these shells of electrons. So does that mean that we've ended up with an atom which is sort of like a solar system, with the sun at the center and planets orbiting the sun? Is it like that, with a positively charged nucleus at the center of an atom and lots of negatively charged electrons buzzing around? Well, that would sort of imply that it was like Newton's clockwork universe, in the sense that if we knew an electron was here, then a little bit later we could predict with absolute certainty that the electron would have moved a little bit in its orbit around the central nucleus. But it was realized very early that atoms are not solar systems. They are not clockwork. We have to throw away the rules of Newton and the ideas of laws of motion and come up with a completely different way of describing how atoms work. So can we think of the electrons buzzing around a nucleus as sort of, satellites buzzing around the Earth? Okay, solar systems are flat, but maybe GPS satellites around the Earth are a slightly better way of thinking of it. Well, no, because it's still clockwork in the sense that if we know where a GPS satellite is, which is obviously quite crucial to make sure GPS actually works, there's no way you can work out your location on Earth unless you know exactly where all the satellites are. So the GPS satellites buzzing around the Earth are clockwork in the sense that we know where they are now and we know where they're going to be a second later, we know where they're going to be a day later, we know where they're going to be a week later. Atoms aren't like that. Atoms do not behave the same way. Atoms are fuzzy in the sense that all we can actually say about an electron buzzing around inside an atom, we can't say where it is, we can't say where it's going, we can't say where it's going to be later. The best we can do is to say, well, we can work out a probability of where the electron is likely to be. Let's just take a very simple atom, an atom of hydrogen, a single proton in the nucleus and a single electron, which we think of as orbiting around the nucleus. But we can't talk about an orbit. All we can really talk about is where is that electron likely to be found. If we were to do an experiment, coming back to Galileo, don't say how it should be, ask if you were to do a measurement, if you were to do an experiment, then where are you going to find the electron? And these pictures here, 8 particular clouds all centered on the nucleus, are bright if the likelihood of finding an electron there is high, and are dark if the likelihood of finding an electron there is low. So each of these clouds is not telling you where an electron is, it's telling you if you were to make a measurement, what is the likelihood that the answer is there, or there, or there, or there. And it's color-coded on a grayscale to give you an idea. So you can instantly see that an electron is not likely to be found at any particular location. It is possible to find it almost anywhere, but certainly much higher, much more likely to be found here compared to be found there. Why should electrons have these weird and wonderful shapes? Well, it all comes from the concept that's at the heart of quantum mechanics, which says that electrons can't just do what they like, they can only have certain allowed energies. This is the idea of quantum in quantum mechanics. A quantum is just a specified discrete amount. And if electrons can only have specified discrete amount of energy, it turns out, I am not going to justify that, but it turns out that the only way you can have that is if the likelihood of finding an electron obeys this particular set of rules. It is not obvious why that is, which is one of the principal reasons that quantum mechanics is not intuitive. Newtonian mechanics, you can say, is intuitive. If you push something, it moves. The harder you push it, the faster you accelerate it. Quantum mechanics is not intuitive because these are the rules that exist on the very smallest of scales, not the rules that you and I tend to obey on the largest scales of millimeters or centimeters or meters or kilometers. So when we're dealing with atoms, how should we describe an atom? Should we use words? Well, particles and waves, I've already said that's confusing, because is an electron a particle or is it a wave? Well, sort of both, or neither. That doesn't help at all. And if we talk about an electron orbiting a nucleus, then we have a picture in our heads which means it's like a solar system. It's not really like a solar system, so we shouldn't really be talking about orbits. And when we talk about an electron spin, we tend to think of it spinning like the Earth spins on its axis, which isn't a very good analogy, so we shouldn't really use these words at all. But what's the option? We have to use some words, so those are the words we use. Would we be better off not using words, but only having pictures? In other words, a picture of electrons going around a nucleus, or a picture of probability clouds, if you like. Well, that one is not very useful, even though that's the sort of picture most people have in their heads. That is more useful, but it's a little bit obscure, so maybe pictures don't help either. There's only really one way to describe atoms. It doesn't involve words and it doesn't involve pictures. The only way to describe atoms, I'm sorry, is maths. Ooh, yes. And that's why teaching quantum mechanics to students means we've got to get the maths sorted out before you can apply that maths to actually thinking about how the world works on the smallest of scales. So that's a little bit of quantum mechanics, which probably means nothing to you, but that's part of the way that we try and work out what's going on the smallest of scales. But of course, we can't just rely on maths, because if you want to teach the maths to a student, you have to use words to explain what it is you're talking about. And usually, you introduce pictures to try and help. But there's no such thing as a concrete picture of what an atom looks like. The best you can do is to come up with graphical illustrations to try and illustrate what the maths is actually telling you. And that's what the problem with quantum mechanics is. You can't really get to grips with quantum mechanics in terms of calculating anything unless you accept the mathematics is, this is the maths that allows you to calculate what the energy of a hydrogen atom is, or why this molecule exists when you bring two atoms together, for instance. That's what you actually need to learn if you want to understand quantum mechanics. You have to start with the mathematics and various other symbolism. Mm-hmm. I'll assume everybody is okay with everything there. Yeah, and this is the sort of thing that you can't introduce a first-year student to. You have to start with the simple stuff and build up to it, and it takes most of the 4 years of an undergraduate degree to teach physics, including whatever you need in terms of quantum mechanics. It's not something that comes instantly, because the students have to be told, this is how you deal with quantum mechanics. Forget Newton. Yes, I know you've been taught about Isaac Newton in school, but when it comes to atoms, Isaac Newton is of no use whatsoever. You've got to move over to a different way of thinking and a different way of doing the maths. Heisenberg, the architect of quantum mechanics in the 1930s. We wish to talk about the structure of atoms, but we cannot talk about atoms in ordinary language for the reasons I've just said. Particles and waves don't really have the meaning you think. Orbit and spin don't really have the meaning you think. When it comes to talking about something, instead of saying the electrons orbit and spin in the atom, you could equally well say the slithy toads did gyre and gimble in the wave. Those two sentences in red carry exactly the same amount of information. Because when we talk about orbit, we don't mean orbit in the sense of a solar system, and when we talk about spin, we don't mean spin in the same sense of the Earth spinning. So rather than use these words, we could use completely made up words and say, well, a toad is defined as this, and a gimbal is defined as that, and a wave is defined as this. And as long as we define what we mean, then you can use any words you like. But unfortunately, because of historical, just the way it is and the way quantum mechanics was developed 100 years ago, we're stuck with words like orbit and spin and atoms and molecules, which sort of make us think they are a little more concrete than they actually are. And it's too late now to throw these words away and replace them with gibberish words, which would be more useful in the sense that you wouldn't have the preconceptions, you wouldn't have the baggage that comes with those words and makes you think about the wrong sort of things. Niels Bohr. Remember, we're talking essentially about a Bohr atom, which is the model of a nucleus in the center and lots of shells of electrons at different distances. But even Bohr wasn't happy with the model that we ended up with. Everything we call real is made of things that cannot be regarded as real. So in other words, we think, that must be real because I can touch it, I can feel it, it makes a noise if I bang it. And yet it's made of atoms, and atoms aren't really real in the sense that they're really fuzzy objects which we can only describe as the probability of them existing in one state or another state. They are not billiard balls. They're not some things that we can predict. Schrödinger, the other architect of quantum mechanics, atomic physics has shown us that atoms have no meaning, but can only be understood in experimental measurement. That is an amazing statement for somebody to make 100 years ago, basically saying, yes, we think the world is made of atoms, that atoms aren't what we thought they were. They are not tiny little billiard balls. They're not tiny little Lego bricks which make up everything that we think of as being solid, for instance. They only make sense in the sense that if we ask what is going to be the result of an experiment, if I want to measure the energy of this hydrogen atom, quantum mechanics will tell us what the answer is. Quantum mechanics is a theory that says if you want to know the energy of a hydrogen atom, follow these rules, calculate it like this, you will find the energy of the hydrogen atom is this much. So you can work out things using quantum mechanics that make sense in terms of an experimental measurement. But in terms of describing what an atom is, it's still something fuzzy which makes no sense whatsoever. I don't like it. I'm sorry I ever had anything to do with it. And again, this is the person that invented it, and you thought that maybe he had a good grasp on the situation. Quantum mechanics versus common sense is the big problem. Common sense is something that you think you know how things work. You think you know what a solid object is. You know that if you let go of an object, it falls towards the earth. Common sense is what you get after 18 years of growing up as a child and getting an education. But when you look at the quantum world, when you look at the world of the very, very small, you find things aren't as you thought. For instance, atoms are unpredictable. We can only ever talk about the probability of something happening. We can never talk about, if this is the way it is now, then I can absolutely predict that in 10 seconds' time, this object is going to be over there. For instance, a billiard ball rolling on a table. If you know exactly where it is, you can say, if nothing else affects it, I know that billiard ball will be here in 10 seconds' time. But when we look at the world of the very, very small, we can't talk about the position of an electron or an atom, or the speed, or the energy. We can only talk about the probability of something happening in the future. And we think of atoms as small, in the sense that everything is made of atoms, so of course they must be small. But when you look at the actual calculations of quantum mechanics, what is the likelihood of an electron, let's come back to hydrogen, there's just a single proton and a single electron at a particular distance from the nucleus. What is the likelihood that that electron is very close to the nucleus? Well, it's quite a high probability. What's the likelihood that that electron is 1 nanometer away from the nucleus? Well, that's a lower probability, but still not zero. What's the likelihood that that electron is 10 nanometers away? Well, it's lower still, but still not zero. What's the probability that that electron is actually 1 meter away? It's very low, but it's not zero. What's the probability that that electron is actually 4 light years away in Alpha Centauri? It's very low, but it's not zero. So an electron which we say is in an atom, in principle, we can calculate the probability that it's close to the nucleus. We can also calculate the probability that it's much further away from the nucleus, and the answer is never absolutely zero. It can be mind-bogglingly small, but that's not the same as being zero. So you could argue that an electron can be anywhere in the universe, and therefore an atom doesn't have an edge. You can't say that the electrons are quite definitely within this sphere. If I've got an atom at this location here, I cannot say that the electron is quite definitively inside a sphere centered on that particular point. All I can say is that the likelihood of it being in that sphere is 99.9999999%, or whatever. There's still a finite possibility it's further away. And another quantum mechanics versus common sense, another ridiculous prediction of quantum mechanics is a particle, or an atom, or a molecule, or a cat can be in 2 states at the same time. In other words, it's like saying the Earth spins anti-clockwise as seen from above the North Pole. But what if it spun anti-clockwise and clockwise at the same time? It just doesn't make any sense whatsoever in terms of common sense. But that is precisely what quantum mechanics is telling us. If we talk about an electron spinning in the sense of, we think of the Earth spinning, well, it can spin one way and it can spin the other way, and sometimes it can spin both ways at the same time. And that sounds ludicrous because our common sense hasn't brought us up to think that way. But that doesn't mean quantum mechanics is wrong. There are lots of instances where quantum mechanics is totally at odds with common sense. And the simplest way of resolving that is to say, common sense is wrong. Quantum mechanics is right. And that takes a little bit of believing, and arguably a few years of quantum mechanics training. Common sense is the collection of prejudices acquired by age 18. In other words, you are born with nothing. Common sense is what you start to build into your world model when you're a child. By the time you're an adult, you think you know how the world works. Only when you start learning about quantum mechanics do you realize that actually the world doesn't work that way and common sense is wrong. Common sense is perfectly good under most circumstances, but if you start to apply it to the very small, the world of the very, very small, you find common sense doesn't work. So if you were to toss a coin, heads or tails, well, we know that if you toss a coin, the answer is either heads or tails. In quantum mechanics, it can be both at the same time, which again makes no sense whatsoever. Einstein never liked this idea that the world fundamentally is based on the probability of things happening, not on absolutes. You cannot say, if I understand what's going on now, then I know what is going to happen in 1 second's time. You can only talk about probability. Einstein never liked that. He thought we're missing something. Quantum mechanics can't be right. It can't be based purely on probability. It only looks like it's probability because we're missing some aspect of being able to calculate what's actually going to happen. God does not play dice. God is subtle, but he is not malicious, said Einstein. Other people diametrically disagreed with that, such as Bohr. So when Einstein said God does not play dice, Bohr retorted with, stop telling God what to do. The universe is the way the universe is, and the universe is based on the ideas of probability. We only think it isn't because of our, quote, common sense. So there were a lot of disagreements in the early 1900s, and it took a lot of back and forth between a lot of very clever people to try and work out what is actually going on in quantum mechanics. Let me give you 3 aspects of quantum mechanics to show you a little bit about how weird it can be. So first, order matters. I'm not going to dwell too much on this, but we know that in algebra, a times b is the same as b times a. 2 times 3 is the same as 3 times 2. Doesn't make any difference which way you put the numbers. If you want to multiply 2 things together, the order does not matter. Same with addition. But in algebra, a times b is the same as b times a, but in quantum mechanics, the order in which you do things does make a difference. And that, again, is against our common sense, because the mathematics of quantum mechanics tells us that the order matters. Not only that, but when we actually try this and do experiments according to the rules of quantum mechanics, we find that quantum mechanics is absolutely right. It does make a difference in which order you do things. For instance, if I was interested in how fast this particular object is moving and where it is at any given instant, it doesn't really matter whether I measure its velocity and then its position, or whether I measure its position and then its velocity, as long as I take it at the same point. But quantum mechanics says it absolutely does make a difference as to which order you do things. Let me show you how ridiculous that is. What if the rules of quantum mechanics on the very, very small actually applied to the very, very large? Let's imagine we had a zoo with 4 animals in it. I can separate those 4 animals in a number of different ways. The top pair, a lion and a vulture, are carnivores. The bottom pair are vegetarians, a water buck and an ostrich. So there's the carnivores, there's the vegetarians. But alternatively, I could have divided those up a different way. I could say that the left pair have got 4 legs, the lion and the water buck, and on the right, they've got wings. Yes, I know the ostrich doesn't fly, but it's still got wings. So I can divide them up into 2 different ways. So let's do a little experiment. Let's pick 2 of those animals out of the 4. For instance, let's do them in a particular order. To start with, let's pick the vegetarians out of these four. If I pick the vegetarians, I get the waterbuck and the ostrich. Having picked those, I'm now going to pick again. So I've made a selection. I'm now going to make another selection out of the same group that I started, out of the pair that I've got there. So of the vegetarians, I'm now going to pick the four-legged animals. So of that pair of vegetarians, I'm going to pick the four-legged animal, which means I expect to get the answer waterbuck. But if this was actually a quantum mechanical experiment and I did exactly the same thing, pick two out of the four, and then from what I get, pick again, I actually get the result of the lion and the waterbuck. In other words, having picked the four-legged animals, it now seems like it's completely forgotten about the fact that I really wanted to pick the vegetarians in the first place. The second measurement, in this case, the second choice, appears to have trashed my earlier knowledge of what happened when I previously made a decision and picked animals out of this zoo. So not only do I get an odd result, but if I pick in a different order, in this case, let's pick the four-legged animals, the lion and the waterbuck. From that pair, let's pick the vegetarians. I would expect to get the waterbuck, but now I get the waterbuck and the ostrich. How can that be? Because it seems to have forgotten about the fact that I started by picking out the four-legged animals. That is the way the world works when you're looking at the very, very small. It doesn't make sense. It doesn't make common sense, but that is the way the world works on the smallest of scales. Perhaps you've heard of Schrödinger's cat. This is not a real experiment. Some people got very upset when they thought that physicists actually put cats in boxes. But no, it's a thought experiment brought up by Schrödinger, who said, what if we had a cat in a box and we couldn't see the state of the cat? And the fate of the cat is determined by, let's just say, there's a radioactive atom, and there's a 50-50 chance that the radioactive atom could decay in a given time period. Doesn't matter what the time period is. Let's say after 10 minutes, there's a 50-50 chance that that radioactive atom would have decayed. And if it decays, then it goes into a little counter, which tells this robot to smash the poison flask with a hammer, in which case the cat dies. So if the box is closed and nobody looks inside, then you could say, well, one of two things happened. Either the 50-50, the radioactive atom did decay, in which case the cat is dead, or the radioactive atom did not decay, in which case the cat is alive. Common sense tells you that even before you open the box, after your 10 minutes, even before you open the box, common sense tells you the cat is either dead or it's alive, but we don't know which yet. And then we open the box and we find one of those two animals, either a live cat or a dead cat. Quantum mechanics says something different. Quantum mechanics says, just like an electron can spin clockwise and anti-clockwise at the same time, if the box remains closed, it's not a question of you don't know yet whether the cat is dead or alive. Quantum mechanics tells you it's both. It's both dead and alive. That is the weird thing about Schrödinger's cat. Schrödinger came up with this experiment saying, well, you might just about believe that electrons behave this way, but if you then use that particle to affect a macroscopic animal like a cat, can we really believe that if we don't open the box, the cat is dead and alive? And it's only when we open the box that the cat is one or the other. Before we open the box, the cat is neither dead nor alive, but arguably a little bit of both. Makes no common sense whatsoever, but rather amazingly, this conjecture has been tested and it has been shown to be correct. Not with cats, I hesitate to ask, but with different systems, it's been checked to try and verify if we don't look at something, is it actually in two different states at the same time before we actually measure whether this object is spinning clockwise or anti-clockwise, or this light is polarized this way or polarized that way. There's lots of different experiments that can be done, and as far as we can tell, it always agrees with this idea that if we were to do an experiment like this, Schrödinger's cat would be dead and alive at the same time, and only when we opened the box to look would we find a dead cat or a live cat. Again, it makes no common sense, but that's the way quantum mechanics appears to work. How do we know it's right? We're saying quantum mechanics has come up with lots and lots and lots of really weird predictions. So why are we following this? Why are we assuming that this theory that was invented 100 years ago, back in the 1930s, why are we assuming that that's correct? Well, we're assuming it's correct because so far, after a century of trying to prove it wrong, nothing so far has indicated that quantum mechanics is not the real state of the world on the smallest of scales. Quantum mechanics regularly predicts things that are impossible by Newtonian mechanics. So we know that Newtonian mechanics is wrong. Quantum mechanics may or may not be the correct answer, but 100 years of testing has not shown any cracks yet in what quantum mechanics is able to tell us. And using quantum mechanics, we can actually build a microscope that can see atoms. We can use what quantum mechanics tells us to build a microscope that works on quantum mechanical principles to actually look at the world of the very, very small. It's called a scanning tunneling microscope, or STM for short. Imagine we have a metal tip, which is much bigger than shown in this picture, but I'm just showing the atoms at the very bottom of a big inverted pyramid. And that is brought close to a slab of material where I'm just showing some of the atoms in this slab of material. Connect the two and make a small voltage between them. No current will flow as long as the circuit is incomplete. If these don't touch, then according to classical mechanics, no current will flow. But when we actually do this and bring the sharp tip fairly close to the sample, we find a current flows. In other words, an electron exists in this region between this metal and that metal, or semiconductor, whatever it happens to be, even though classical mechanics says it is impossible for an electron to exist in that particular gap. Quantum mechanics says, yes, it is possible. And if you actually to move the tip across the sample, so imagine the tip's in this position or the tip is in that position, imagine the sample was not absolutely dead flat, but you can see the sample is made of atoms, and these atoms are not absolutely level, there's some variation. You can see that if we were to move the tip absolutely level, the distance from the tip to the sample would change slightly. And quantum mechanics tells us that the smallest of changes to the distance between the tip and the sample gives rise to a big change in current, which is something that we can measure. So what we actually do is move the tip and we try and keep this distance fixed. In other words, the tip actually traces out the profile of what the sample is that we're looking at. So we move the tip across the sample and measure the current at each point. So there's a rather handsome individual standing in front of a scanning tunneling microscope. The microscope is inside a vacuum vessel to try and keep the tip and the sample clean. We don't want lots of atoms getting in the way of our tip approaching the sample. So we have an ultra-high vacuum vessel at a pressure of about 10 to the minus 13 atmospheres to keep it nice and clean. And when we do that, we can get pictures like this. Notice the scale here, that is 2 nanometers, that scale bar. So you can see we're talking about very small scales, and each of these little mountains, the vertical scale has been exaggerated for clarity. Each of these little mountain peaks here is a single atom. This particular surface happens to be iron oxide. And you can see the arrangement of atoms. The atoms seem to want to arrange themselves in these little islands, and the islands seem to be separated from each other. If you look at it, you can actually see the islands are in a particular pattern, as well as the atoms within an island being in a particular pattern, the islands themselves are in a particular pattern as well. So this is actually 2 phases of iron oxide. Yes, sir?
Is that microscope the same as an atomic force microscope?
It's based on similar principles. It's not quite the same. An atomic force microscope is measuring the force, but it is corrected to say that it's a tip that is brought very close to a surface. And again, it is very sensitive to the distance between the tip and the sample. In the atomic force microscope, it's actually sensitive to forces between the two. Here, it's actually looking at a process called tunneling, in which the electrons exist in the gap between them where they should not exist according to classical mechanics. So they're very closely related. Yes? So here we have a pattern of atoms within an island, and the islands are separated by in a particular pattern. This is iron oxide, and what we're actually looking at are, I can't actually remember which way round this is, either these islands are either Fe3O4 and these regions in between are Fe2O3, or the other way round. I've now forgotten which way round they are. So different phases of iron oxide give rise to atoms that are very easily visible in terms of their height, or are relatively low, rather smooth areas in between these islands. The same elements are there, iron and oxygen, but in a different arrangement, giving rise to different heights of these mountains. And when we actually look with scanning tunneling microscopy, or indeed atomic force microscopy, we start to see patterns in how atoms are arranged. So again, we are at a scale now of only a few nanometers, so we are seeing individual atoms. Perhaps you can see that some of these patterns are sort of a daisy pattern of 10 petals, if you like, around this circular region. But also, the more we look, the more we realize that, oh, actually, we've not only got 10 petaled flowers, we've actually got 5 petaled flowers in there. We've got pentagons. So some of the atoms are actually arranged in pentagons in this particular material, which on a macroscopic scale looks like that. That is why we get pentagons. When we look at a crystal on a millimeter scale and look at these crystals, we get these pentagons because the atoms are arranged in pentagons. Again, it wasn't obvious until relatively recently, but again, this was telling us that the only way to get atoms to arrange themselves into a crystal like this is that the individual atoms must be arranged in pentagons and decagons, etc. Now we have the microscopes, thanks to quantum mechanics, that allow us to actually see those individual atoms and confirm that, yes, now we understand why we get crystals like this on the macroscopic scale. Not only that, but we get a few curiosities as well. If we look at the distances between atoms and measure distance between some atoms and the ratio of that distance to some other distance, I don't know which particular ones we should be looking at here, but if you take ratios of one distance with another distance, a particular ratio keeps cropping up with these particular materials. The ratio is 1.6 and a bit. This is the same ratio as if you take a pineapple and count the number of scales this way and count the number of scales that way in the two spirals that exist in a pineapple, then the ratio of those two is approximately 1.62. Do the same with a sunflower seed head. You can see two sets of spirals. If you count the seeds in one spiral and count the seeds in the other spiral, take the ratio of the two, you get 1.6 and a bit. That number seems to keep cropping up, and some people are studying why is it that atoms on nanometer scale seem to obey this particular sort of golden rule, if you like, and that seems to be mirrored in some aspect of the arrangement on macroscopic scales. So there's probably something very interesting going on there, but we're not necessarily sure what that is right now. But I'll finish with an image like this. Just one more slide after this one. This is an arrangement in which lots of atoms have been arranged into a circle. I haven't talked about this, but it is possible to use techniques such as atomic force microscope or scanning tunneling microscopes, not only to measure what is going on in terms of the atomic bumps on the surface, it's also possible to use this tip to move atoms around. You can bring the tip down and nudge an atom along and then lift it up, and then bring it down and nudge an atom along. So you can actually arrange atoms on a surface. And in this particular case, a corral, a large circle of atoms have been arranged, and then the tip has imaged what it then produced. And you see that you get this sort of mountain top of lots of these spikes that look like teeth around the edge. They're a lot of individual atoms. But what's going on inside this corral? It doesn't look like a lot of individual blobs inside the corral. It looks like the sort of effect you get when you throw a pebble into a pond. It looks like the sort of ripples you get whenever you have waves on water. So in this particular image, we seem to be establishing that atoms are behaving like particles here because they're at that position, that position, that position, that position. But what's going on inside is that either the electrons or the atoms seem to be behaving like waves. In a single image, we've again captured this dichotomy of should we be describing these things as particles or should we be describing these things as waves? This single image tells us, well, it looks like both at the same time, depending on the circumstances. Very confusing. If quantum mechanics hasn't profoundly shocked you, you haven't understood it. This is something we tell our students continuously. That's no excuse for not passing the quantum mechanics exam at the end of 4 years, but anybody who thinks they understand quantum mechanics hasn't been paying attention, because it makes no sense whatsoever, and the only thing you can do is to say, well, it appears to work. We really don't understand why. Why does the universe obey a set of rules which appear so ridiculous? The only thing we can come back to is that our common sense has not equipped us to deal with quantum mechanics. We've only had 100 years to try and get used to the idea of what quantum mechanics is telling us. Maybe at some point it'll be overthrown. Maybe after a little while we'll get used to the fact that yes, quantum mechanics is the way it is. We're going to have to start teaching kids earlier so that common sense doesn't get in the way of understanding how the world actually is. But this is one of my favorite quotes from Einstein. The most incomprehensible thing about the world is that it is comprehensible. So we are just monkeys who came out of the trees 1 million years ago or whatever, and yet when we look at the expanding universe or when we look at atoms, it is actually possible with a little bit of effort to understand the way the world is, either on the macroscopic scale of the universe or the microscopic scale of atoms and molecules. The most amazing thing is that we can make any headway whatsoever, given that we are just monkeys with a little bit of practice applying our brains to interesting problems. Not one of my images, but I love this image. Look at the scale, 850 picometers. So that is less than 1 nanometer. So that's less than 1 nanometer across here. And we're looking at a few atoms here. These are atoms of carbon. 1 atom of carbon, another atom of carbon, another atom of carbon, etc. If we were to imagine on this scale a grain of sand, imaged at this scale, at this magnification, if you like, a grain of sand would be the size of the moon. That gives you an idea of the magnifying power of a scanning, tunneling microscope. And whenever I look at individual atoms and imagine how big a grain of sand would be, I always think of William Blake. To see a world in a grain of sand and a heaven in a wild flower. Hold infinity in the palm of your hand and eternity in an hour. Thank you all very much.